All right, what up, everybody? Today we're talking about transverse waves, and transverse waves are the type of waves where you see whatever medium it is going up and down. Right? Probably one of the easiest types of transverse waves to visualize is a wave on a string. So we're going to talk about use the wave on a string as an example. And so you see in this picture, this is a string, and just imagine the string is being held by something on each side. And the string is flat. And the reason it's flat is because there's no energy going through it. Now, if one person were to start shaking this string, then the string would look like this, right? And you see a wave pattern. Part of the string would go up, part of the string would go down, and then the part that's up would go down, the part that's down would go up, and it just keep on moving. And the reason it's moving is because you have given the string energy by shaking it, right? And that's all a transverse wave is. A transverse wave is where you add energy to something, and as a result, it kind of goes up and down in a string in a wave pattern. So, just some vocabulary words that we need to know. The top of a wave is called a crest, and the bottom is called a trough. Right. So we'll be using those words. They're just fancy words to mean the top and bottom of a wave. Right. Um, if you can imagine that you're holding both sides of a string and you're shaking one end of it, and you keep on shaking it till you get to the right frequency where you see like 4 bumps form, right? And then you shake it a little bit slower. You see 3 bumps. You shake it a little slower. You see 2 bumps. You shake it even slower. You see 1 bump, right? And if you never tried this, you can get a string and try it. It works. These are called standing waves, and they happen at a certain frequency. If it's not one of these special frequencies, then you won't see the bump stay in one place. But if you find one of these special frequencies, you'll see the bump go up and down and stay in the same location. Right? And what happens is there's parts of the wave that are continually going to go down and up, and there's parts of the wave that are going to stay right in the middle. Okay, we call these places in the middle the nodes. And the nodes are where the wave does not move up and down. Okay, if you can imagine you're just like if you're a tiny little bug who's been glued to a string, if you're sitting on one of the nodes, it's going to just be kind of like you're in the middle of a seesaw, right? You're going to rotate up and down, but you're not going to actually move up and down. Um, The antinodes are the parts in the middle of these bumps where the string goes from the very top down to the bottom to the very top again. If you were a little bug that was glued to one of the strings and you happen to be glued right at an antinode, then you'd be in for a wild ride because you go up to the very top, down to the very bottom, up to the top again. Okay, so those are called antinodes. Another part of a wave that we pay attention to is what's called the equilibrium position. The equilibrium position is where the string would be if there's no energy, right? And you can see the black dotted line. If you stop shaking the string and this gave it time for the friction to cause the movement to disappear, then eventually the string would go back to being a flat string and it would rest right here on this black dotted line. Okay, so that's called the equilibrium position. And it happens to be right in the middle, halfway in the middle between the crest and the troughs. Amplitude is a measurement of how tall a wave is. Amplitude is measured from starting from the equilibrium position up to the crest, or starting from the equilibrium position down to the trough, right? Either way, it's the same height. Okay, the wavelength of a wave is another way to measure the size of a wave, and that's measured from one part of a wave to the exact same part of the next wave. So remember, each wave has a crest and a trough. So you see on this picture right here, there's actually 2 wavelengths. It starts here. There's a crest, there's a trough. There's another crest, another trough. Right? So there's 2 wavelengths. Right? But if you measure from the top of one, then you have to go to the very top of the next one to find how long that is. Right? Or you can go from the trough to the next trough you see. As long as you're going from one point to the exact same point on the next wave, then you can measure the wavelength. Right? So in this case, we start at the equilibrium position. There's one crest. You're back at the equilibrium position, but it's not a full wavelength yet because you're going down, not up. So you keep on going through the trough, and then you go up again. And then we're back at a equilibrium position. and you're going up. So that's the next, that's the identical point on the next wave. So that's where you would measure the wavelength. Okay, so that's the parts of a transverse wave. I'll see you all in the next video.